I'm very happy everybody come here for today's lecture, for today's EP lecture. And this lecture was established in 2019 by Dr. Yip. And the purpose is to give lectures on mathematics, physics, psychology, and physiology. And we would like to thank very much of Dr. Yip Xin Yu for his generous donation for this lecture. And I think there's Peter is supposed to introduce the speaker. Thank you.
It's an enormous pleasure to welcome you all here today to hear our colleague, my friend, Andy Strominger, who's going to be speaking. And I've known Andy since since the trilobites ruled the earth when we were undergraduates. And ever since it's been a pleasure to work with him, to see his luminous presence in the physics department as he draws together generations of undergraduates, graduate students, postdocs, and colleagues who all enjoy and have produced such remarkable work together with him over all this time. Andy loves structures at the intersection of mathematics and physics. He did work with Ed Witten that helped bring the connection clear between particle physics and string theory. With Qumran Vafa, he collaborated in figuring out how to give a microscopic account of all the different states that could be found around a black hole and get the number right, even down to the famous 1/4 that Stephen Hawking had predicted. In more recent work, he's looked at the connection between quantum field theory and gravity to find another way of counting those states, but without string theory. He's a co-founder with Shep Doleman, who's here, and me, and Ramesh Narayan, and Avi Loeb, Xingtung Yao, of the Black Hole Initiative. He's done many things. He brings a huge amount of light and excitement to the field of theoretical physics, and it's a pleasure as a friend and as a colleague to welcome Andy Strominger to give this year's EP lecture.
Thank you for the very kind introduction, Peter. And it's great to be here. One doesn't often give a public lecture in a home territory, and it's great to see so many friends. And hello to everybody out in webland. Okay, so I'm going to talk about black holes, the weirdest objects in the universe, and this is the lecture. So in the last several decades, 50 years ago, when I was an undergraduate, there wasn't so much talk about black holes. But in the last several decades, they've really come to center stage in many different ways. It's both become an exciting observational science. When I was in college and graduate school, many people thought that black holes didn't really exist because they hadn't been seen. But now we've really seen a picture of them, thanks to Shep. I think that was the moment in which the last skeptic Shep and his wonderful crew, the last skeptics gave up on the idea that they didn't exist. And at the same time, there's been mounting consternation, interest, excitement, and a lot of hard work on trying to understand what these things are that we're seeing. And it crosses many areas of science. So they're very interesting for people who want to understand the synthesis of quantum mechanics and gravity, among whom I count myself one, because they are it is the place where quantum mechanics and gravity battle, and it's the most interesting and rich kind of Gedanken experiments that we can do. There, of course, it's just an exploding observational subject at the Event Horizon Telescope and elsewhere. Philosophers are wondering what it means to have a region of space that we can't see. The gravitational wave observers are measuring their signals. Of course, that was even before the EHT, that we had indirect sighting of them through the gravitational wave emission. They have very deep mathematical properties, and they're just understanding their properties has spawned whole areas of mathematics. There are many deep theorems, rigorous theorems about how they behave and what they can do and what they can't do. Their history is really bizarre, and with lots of twists and turns. I'll say a little bit about it. In computer science classes now, I don't know if any of you are taking them, but black holes provide examples of things that could compute, saturate some kind of various kinds of information bounds. And they have also, their behavior has given us ideas about what things might be true in computer science and information theory. And string theorists, of course, also are interested in them because they have constructed examples of black holes that really can be understood in complete detail. So let me start with a very elementary description of what a black hole is, going back actually to the 19th century, before Einstein. So if I'm on the Earth, and I mean, I can't do it, but if I'm on the Earth and I can accelerate and get up to 11 kilometers per second, then I can escape the Earth's gravitational field, ignoring friction, ignoring the ceiling, so on, and just go on forever into outer space. That's escape velocity. On the moon, which is less massive, I only need to do 2 kilometers per second. And the more mass you have, the larger your escape velocity is. So way back in the 19th century, it was hypothesized that things could exist which had such a strong gravitational force that the escape velocity was greater than the speed of light. And if it's greater than the speed of light, you can't see it because light can't come out of it. Now, a little bit after that, Einstein explained to us that nothing can go faster than the speed of light. And so, in fact, nothing can get out of a black hole. Now, the history of our understanding of a black hole is, first of all, far from over. The most interesting part of it is yet to come. And I hope to give you hints of that in this talk. But the history of it was really kind of fantastic. So Einstein wrote down his equations, which are nonlinear, very difficult, the worst, gnarliest kind of mathematical equations you can write down. And it was thought, apocryphally it said, that Einstein believed that no one would ever find a closed form solution. But a few months later, and a few months before he died, just before he died, Schwarzschild found a solution, and is a black hole. But black holes are so strange and confusing. Now, so usually, it doesn't usually go this way in physics. When you solve the equation, that's the hard part. You do the math, you do the hard part. Then understanding what it means, you just kind of chisel away at it, and eventually it makes sense. Not so for black holes. So, in fact, almost 35 years later, there's a quote. Einstein wrote a paper saying that black holes don't exist. And there's a quote in there which would flunk him out of my general relativity course, or anybody else's. Took a long time to understand general relativity itself, and it's a little bit mind-boggling that Einstein would have said that, but it's all there. It's all there in print, and it's just they're just very strange objects. And some of the certainly the greatest physicists of the time all wrestled with this. Nobody really understood it. And it took 60 years, really a long time. And this was 60 years. There wasn't more experiment needed. The equations were there. They just had understood what it meant mathematically. It took 60 years to understand it. A language had to be developed for properly describing it. And it was summarized in work by the Wheeler School and the Penrose School, the laws of black hole thermodynamics, Hawking, Carter, Christodoulou, Thorne. So somewhere around the 60s, we began to understand what a classical 60s, early 70s, really, we began to understand what a classical black hole. Now we believe we orbit around one. And on top of that, we think that if you step outside and look up in the sky, there's millions of them up there. They're everywhere. And we don't understand them. So what the kind of part of the summary of what a black hole is, the summary of what a black hole is nothing. So in this room, there's air. You can't say the room is empty, there's air in there. But you could go into outer space and then you would have a vacuum. But there's still the vacuum there. The vacuum is a thing, you can hit it, it'll bounce back. There's something there. But there's a sense in which there's absolutely nothing inside a black hole, that space itself has come to an end. And so what black holes are is just a round hole of nothingness. And it's very different from a star. Of course, they're made out of collapsed star. But if you have two stars of the same size, they're very different. Their detailed chemical composition will be different. The motion of the individual atoms will be different. The magnetic currents will be different. Every star of the same mass, they may be the same in their grossest property, but in detail, they're different in myriad different ways. Not so with black hole. According to our understanding then, every black hole was characterized by two quantities, the mass and the spin. They can also spin around. You could also have charge, but that would tend to get neutralized. And John Wheeler, who was the master of great phrases and names, came up with the phrase to describe this, that black holes have no hair. They have no distinguishing features. They're the boldest, most primeval, simplest object you could imagine. Okay, so just when the classical story finally was coming to some peaceful resolution in the early 70s, Hawking threw a monkey wrench into the whole thing. And he said, what happens in a world with quantum mechanics? How do black holes behave? And he discovered, he inferred through an incredibly simple, ingenious argument, that black holes actually radiate. And the radiation is so-called black body radiation, like what comes off a hot stove. It's a certain kind of mix of different frequencies associated with a temperature, and it's characterized as black body radiation, and its temperature is, it's a thermodynamic law that its temperature is related to its mass or energy by this formula involving Planck's constant, 8 pi, and Newton's constant, and the mass of the object. So they radiate everything. They're not completely black. Large ones radiate very slowly. And this is a quantum effect. One way of understanding it is that in quantum mechanics, everything is uncertain. And even the position of the event horizon, the region from which light can't escape, is subject to quantum uncertainty. And a lucky particle can be sitting there inside the black hole, and the event horizon can fluctuate in and it can jump out. Okay, so in what is really one of the most beautiful unifications and episodes of the history of physics, Boltzmann showed that the laws of thermodynamics, so what are the laws of thermodynamics? They are laws like, if I put a quart of water on top of the stove and turn the gas on medium, it will boil in 3 minutes. If I put it in a pressure cooker at a certain pressure, it will boil in fewer minutes, longer minutes. So those are thermodynamics laws. How much temperature raises when you change the energy, when you change the heat. These were all thought to be basic laws of nature in the 19th century. What Boltzmann showed is that assuming that everything has a smallest component, molecules or atoms, that all thermodynamic laws can be explained by statistical reasoning. Like if you have a lot of pressure, you push all the air and gas to one side, there aren't as many statistical possibilities, so they want to jump out to the other side. And so he really explained a lot. And a key ingredient in his reasoning, which was applied to everything, really, is the notion of what he called entropy. We could also call information or gigabytes. And it's the log of the number of configurations. So, if your smartphone has 64 gigabytes, that's telling you how much information it can store. There's some chips in there, and they can be up or down or on or off. And there are that many different configurations that it enables it to remember things and store information. Okay, so now, the ultimate goal of a physicist is to have a great equation they want to put on their headstone. And I actually, maybe Peter knows more, I actually know 4. This is 2 of them. There's 2 over at Mount Auburn. Not too many people have achieved this goal. But so here's Hawking's at Westminster Abbey, equation for the temperature. Here's Boltzmann and Zentralfreudhoff in the cemetery. It's the formula for the number of gigabytes of a system. Now, if you take these 2 great formulas, certainly 2 of the most important formulas in the history of physics, and you put them together, you get a formula for the number of gigabytes in a black hole. And that's what I've written there, the formula for the number of gigabytes in a black hole. So this should be directly translated. Your smartphone has so many gigabytes, your laptop has so many gigabytes. This is how many the black hole has. I promise you the black hole wins. It's a very big formula. All of the gigabytes in the Google database would fit inside a black hole, which was a trillionth of a millimeter, smaller than anything we can imagine. So they're fantastic storage devices. Now, but one thing I want to say before we pass from this formula is we're pretty sure it's true, and we're absolutely sure we don't really understand it, where it comes from and exactly why it's true. And it's an unusual formula because it's not like the Schrodinger equation, which tells you how quantum systems behave, or Einstein's equation, which tell you how space-time curves for matter, or Maxwell's equations, which tells you about light behaves. It's kind of an equation which it involves all the different areas of physics. It involves statistical mechanics from here in the entropy or information. It's geometry, it's got the area, it's got h bar for quantum mechanics, gravity, Newton's constant. So it's a formula which is lying between all the understood laws of physics and connecting them. And we don't really understand I imagine that 100 years from now, we'll start with this formula instead of starting with, and everything else will follow from this formula or some better version of it, because it's such a universal formula which applies to so many things. And in fact, it applies to the universe itself. The universe itself has a horizon that light can't pass, it's the so-called cosmological horizon. And this formula with the same coefficient also applies to that horizon. Now, there's a conjecture or a law called Moore's law that the information that you can fit on a chip of a fixed size doubles every 3 years. And this has been sort of amazingly true for the last several decades. But if what we believe about black holes is correct, this is doomed to failure, though we have to wait 300 centuries. Because there's a bound. If it continued for, 300 years. If it continued for 300 years, the chips would have as much information as a black hole. And at that point, all our smartphones will have little black holes inside them. And nobody will ever be able to build a better smartphone. Okay, so now if you are listening carefully, you'll realize that I told you two things which were exactly opposite. One is that the black holes are the simplest, most structureless objects that one could even conceive of. And the other one is that they were the most complicated objects possible. They like both extremes, and they manifested both extremes in different contexts. So how is it possible for one object to be both the simplest thing in the universe and the most complex thing in the universe? And this is the puzzle that Stephen Hawking presented us with in 1974. And how are we supposed to reconcile this? And I think I won't try to describe it in detail, but there's a not very difficult thought experiment which tells you that if both of these things are true at once, information is destroyed, which is tantamount to saying that there are no laws of physics, because the laws of physics tell you how to go from configuration to configuration A to configuration B in a supposedly unique manner. And if there were no information inside a black hole, that would not be possible. And this has been, when a puzzle comes up in physics, of course, we never know. Some things seem like puzzles, they come up, but then they turn out to be essentially technical in nature, and we go on, we solve it, and we go on, and we forget about it. But then there are other important puzzles that we don't solve. And this one we've been banging our heads on for 50 years now. And the longer we do that, the more persuaded we become that there's something really, really interesting going on here. And we're going to have to think about the world in a very different way in order to completely solve it. Of course, we never know till we do that. Could be that we just lost some factors here and the whole thing goes away. So then string theory came along and had something to say about this. So what did string theory have to say? Well, this problem involves quantum mechanics and it involves gravity. It didn't appear until Hawking started thinking about how quantum effects change the behavior of a black hole. And string theory is, the the main theory that we know about that includes, it might or might not have something to do with the real world. It's not what we're asking here. It's a theory that includes quantum mechanics and gravity in a otherwise seemingly consistent manner. And it's the theory we have a lot of mathematical control over. And we have tools in string theory to address this problem that we don't have in general. And so what we found after many years of work was that certain black holes in string theory could be described in two complementary but completely equivalent ways. So what do I mean by complementary? Well, we could say that this bottle of water is 3/4 full, or we could say it's 1/4 empty. And those would be the same statement. And you would recognize it right away that those statements were equivalent. But there are other cases where things are equivalent, where it might take a little while to figure it out. And then there are cases where you might have to found and solve some new kinds of areas of mathematics in order to show the equivalence. So things where it takes years to understand the equivalence. And this was an example where showing that these two pictures were equivalent took years. So we have now an example, an existence proof of where everything is consistent. The black hole indeed has a lot of gigabytes, and we have one description where we can take it apart and we can count all the gigabytes, and it matches perfectly. And if this hadn't worked, string theory would have been inconsistent. Okay, now, as is often is the case, in the original calculation was done in the most unimaginative, straightforward, and tedious way. It sort of reminds me of the Lewis and Clark documentary I was watching the other night, where they went to the Great Portage. They portaged for a month. They went down the Rockies, 100 miles, went around, went back up, found the Shoshone Indians. They'd been looking for them, and they told them you were 4 days away from where you started by walking. That's something that happens a lot in science. And it happened here. And what it turned out is that there was a symmetry underlying all of it, a symmetry called conformal symmetry, which appears all the time in the real world, in laboratories over at Jefferson and Lyman, appears in the early universe. It's kind of the favorite symmetry of physicists and engineers. And it's a symmetry which has the property, now it's a property that things look different as you change their size, as you zoom in or zoom out. So this is a picture of a spiral, and you could just keep going forever. So this spiral has conformal symmetry. You just keep going forever, you keep zooming in forever, and it still is exactly the same size. Now that wouldn't be true in this room. If I zoomed in, I'd be in your jacket there, and then I'd be inside your, it doesn't look the same on all scales. But in fact, there are regions of the universe now that we've found pretty uncontroversial evidence for, where this symmetry exists, where space-time is curved in such a way that the conformal symmetry is a symmetry of space-time. And where do we get those? Well, wonderfully, they happen in black holes. And so black holes can spin, but there's a speed limit on how fast the horizon can go. It can only go at the speed of light. And once they go at the speed of light, everything has to go around the speed of light. They become very simple. And at the same time, in this limit, there's a conformal symmetry, a scale symmetry that emerges in the geometry near the horizon of the black hole. And this is the same thing that happened in my calculation with Vafa. And for these very special types of black holes, which are rare, but they do exist. Here's some that have been seen that are very nearly extremal. We can understand the gigabytes in a black hole in a similar manner. But we still want to understand the most general form. We want a still better understanding of that. And we still want to understand the most general form of how we think about entropy and how we think about Hawking's paradox and the number of gigabytes for a general black hole. And don't hold your breath. I'm not going to answer it in this colloquium. We don't know it. It's not a solved problem. But it's clear that conformal symmetry plays an important role. And recently, we've been talking to astronomers a lot, particularly with over the Black Hole Initiative, where there's a bunch of people here from the Black Hole Initiative, and so they, of course, produced this spectacular image, which poked us in trying to understand this. It made us think about the world. We know when you see something, it's different than when you write it down on a paper. And so that made us think about things in a different way. And talking with them, we came up with a prediction that that M87 star, which they saw, is surrounded by so-called photon rings, which I'll explain in a minute. And we hope to observe these in upcoming experiments. And these photon rings have a conformal symmetry. So there was a paper about this a couple of years ago. I'd just like to give a shout to Michael Johnson, who's sitting in the second row. He's also one of the heroes of the EHT, and also Dan Kopetz, who's fielding the questions at the end, and Alex Lipsaska, who played a role, and of course Peter here, who introduced me, and Shep, and many, many more people here are here. It's a great group over there. And so what is this photon ring? Well, there's a nice movie of it that that was made over at the Black Hole Initiative. And in this picture, this is a black hole. This is supposed to indicate the curvature of space around the black hole. And then in a minute, when I start it, light rays are going to come in, and they can get caught orbiting the black hole. So it turns out that a light ray can't orbit the Earth, but a light ray can orbit around the black hole forever. And what happens is that some light rays will come in and orbit some number of times, and then hit the screen where the Event Horizon Telescope has set up all their observing devices. Okay, there's one. So that one isn't orbiting. These are called the n equals 0. But now we have the ones that orbit a half a time. That's n equals 1. And they're focused at a particular point. And now they all have to fall in a ring. The geometry, this is a hard calculation or computer simulation to show that they form thinner and thinner rings with higher and higher winding numbers. So this is a very striking feature of the geometry of curved space around a black hole. So this stuff, which is what's mostly been seen so far, the light is coming directly from us. So if we look back at the EHT image there, all of this light just came directly to us from the black hole. And we're in the best situation you could possibly be, because we're just on the edge. In fact, people even argued about whether it could be seen in the data already. I think not, but there were intelligent people who were arguing that if you analyze the data in the right way, you could see it. So it's just on the cusp of being seen. So we just need to get slightly better observational technique, and then we'll be able to see lying in here these fine rings of light that, unlike this one, they're not telling us. This one, basically, we're seeing the matter orbiting around the black hole, and most of the information in here is information about the matter, not about the black hole itself. And when you see the orbiting images, you're learning about the black hole itself. It's as if you're, if you go to a department store mirror, the hall of mirrors, and you look directly in front of you, you see what you're wearing. What you learn is whether the outfit looks good on you or not. But if you look at the subsequent images, you learn about the geometry of the mirrors. You can't really learn about the geometry of the mirror just by looking at one image. And it's the same way in the black hole. If we see these subsequent images, we're really learning a lot. So let me draw yet another picture of it. It's a little hard to understand this, so I'm drawing it in different ways. So here's the black hole, and here's a person standing, waving, and this is the n equals 0 image, where the light comes directly from the person. Now here's a second image, the n equals 1 image, where the photon went around behind the black hole and orbited around and then came back. It's not a 3D laser. And then it came back out at you. And the head would go down in orbit like this, and the feet would go up and come like this. So the image gets inverted. But then, what's this one here? Well, this is the one where it goes in front of the black hole and orbits around and comes out right side up. And one full orbit. We call that n equals 2. And here's where it goes 2 full orbits and so on. And so you get an infinite sequence of images. Now it turns out that these images we've been able to show mathematically that these images are related by conformal symmetry. And that conformal symmetry, in some limits, becomes equivalent to the other conformal symmetry that we use to explain, that we use to compute the number of gigabytes that there are in a black hole. So we haven't solved this problem, but there are a lot of interesting facts that we're struggling with, and we keep learning new things. Okay, so now actually we have a new production in beta, and you're the first test audience. My friend and student Dominic Chang developed this. Now, I want to say we want to do better, but to do better, I've got a camera here. We actually need a 4-pi camera to get a good rendition of the photo ring. And I hope that next time I give this lecture, we'll have gotten the 4-pi one going. So what I'm going to show you, okay, Dominic, if you could kind of stand there and wave, okay, and walk down and come. So notice how his image is over there. And he's going, it's upside down. It's going down, and but he's right side up there. That's an odd image. So this is literally what you would see if there were the black hole. Actually, this would be the point of no return, where the so-called, this is the photon ring here. This is the point where the image is accumulated. And if you go closer, the black hole is actually just in here, but if you go closer, if the light from your face goes closer, it just gets sucked into the black hole. So this is literally what you would see. There's an infinite number. A black hole is like an infinite mirror because the light from your face can go to the black hole in orbit as many times as it wants before coming back to you. But those images get squeezed in closer and closer to the photon ring. So this is really, our universe is a really strange place, and there are parts of our universe where really weird things happen. And black holes and their near horizons are pretty high on the list of weird places. And now there was a dramatic, with the Event Horizon Telescope, 2 orders of magnitude improvement on what we could see. And we're hoping in the near future that we can see this guy. Okay. Now, in order to do this, so the Event Horizon Telescope totally maxed it out. In other words, they made a telescope that was as big as the Earth. And so, well, you can still improve that by putting in more of the Earth, but probably to see the photon ring, we need to put some extensions in orbit and have them synchronized. And so I think it's going to be a big project in science in the next, in the coming decades, to see this photon ring structure, which is really sort of the hallmark of a black hole. So I'm going to end there. And I just want to say that, we're trying to understand black holes. We're trying to understand quantum mechanics in black holes, string theory. We're led in all kinds of different places. We talk to astronomers. They make us think about things in new ways. And who knows how we'll ever get there or how we'll ever understand everything. But we sure feel like we're moving. Thank you.